To build a rigorous foundation for discrete mathematics, we begin with the concept of a set. At its simplest, a set is just a collection of distinct items grouped together. We manipulate sets using basic operations. A union combines sets, an intersection isolates shared elements. Difference removes elements of one from another, and the complement captures everything outside. Building complex logic requires defining connections between these distinct, separate collections. This is where we move into the study of relations. These mathematical structures record how elements from one set interact with another. Mastering this logic allows us to translate abstract, real-world connections into rigid mathematical structures that a computer can process. The first step in constructing a relation is the Cartesian product, written as A cross B. This operation takes two sets, pairing one element from the first with the second. The Cartesian product is exhaustive. It generates a new set containing every possible ordered pair formed between the two parent sets. Because these pairs are ordered, the sequence matters. The pair 0, 1 is distinct from 1, 0, as each position refers back to a specific parent set. This pairing mechanism creates a coordinate space, treating set A as the horizontal x-axis and set B as the vertical y-axis. Multiplying the natural numbers by itself yields a discrete coordinate grid. Crossing the real numbers with itself forms a solid, continuous geometric plane. This logic scales to any number of dimensions. We can cross 3, 4, or n sets to create triples and quadruples that accommodate any number of variables. Pythagorean triples are essentially valid coordinates residing within a three-dimensional Cartesian product of n cross n cross n. The Cartesian product provides the total universe of possible pairings, the dimensional field where we can map out specific relationships. A mathematical relation is defined as a subset of a Cartesian product. To isolate specific pairs, we use set comprehension. Filtering natural numbers where the second is 1 plus the first isolates a specific subset. On a continuous real number plane, filtering for points with a distance of 5 from the origin perfectly defines a circle. In formal notation, stating that a pair A, B belongs to relation R is functionally the same as writing ARB. This filtering logic applies to any data. A school administrator identifies specific teacher course pairs from a pool of potential assignments to create a functional schedule. Biological connections fit this model. We filter the product of all people for the exact subset where person A is the mother of person B. Relations allow us to filter infinite possibilities into exact logical structures, whether we are defining geometric shapes or familial lineages. When a relation connects a set to itself, it is often easier to visualize the data as a network of nodes connected by directional arrows. This network view highlights specific properties, like reflexivity, where every single element is related to itself. Division is a reflexive relation because every non-zero number divides itself. The second property is symmetry, where direction doesn't matter. If A is related to B, B must be related to A. In an anti-symmetric relation, reverse connections are forbidden. For example, if 5 is less than 10, 10 cannot be less than 5. The third property is transitivity. Here, independent connections bridge together to form new, guaranteed logical links. If 2 divides 6 and 6 divides 36, the transitive property ensures that 2 must divide 36. When a relation is simultaneously reflexive, symmetric, and transitive, it generates a structure that mimics the properties of equality itself. A relation that satisfies all three properties is known as an equivalence relation. This specific combination of properties results in a partition, dividing the original set into disjoint groups called equivalence classes. Modulo arithmetic offers a clear look at this partitioning process in action on the set of integers. In a modulo 5 relation, integers are related if they share the same remainder. Applying this filter snaps the integers into 5 separated clusters. Within the remainder 2 class, numbers like 7 and 12 are equivalent, sharing no connection with any other cluster. This allows us to group infinite data into a finite number of states, based on a specific definition of equality. We use the logic of equivalence classes every time we check a clock. A standard clock acts as a physical equivalence relation, partitioning the 24 hours of a day into 12 pairs of identical states. On a 12-hour cycle, 2 a.m. and 1400 hours belong to the identical equivalence class. The hardware treats them as functionally the same. We rely on these mathematical partitions daily, using external context to distinguish between members of the same class. From discrete coordinate grids to modular arithmetic, the logic of relations defines the rigorous framework used to organize and process complex systems of data.